How about the magnetic field energy in your inductors? Inductors store energy in the magnetic field, which is given by your U, your magnetic field energy, that's equal to 1/2 of the inductance times the current I squared. The units of your U in joules, which is equal to your energy. Remember that for your resistor with current I, energy is dissipated. For your inductor with current I, energy is stored. Now let's talk about your LC circuit. An LC circuit contains an inductor and a capacitor and is an oscillating circuit. What you have here is an example of an LC circuit. You have an inductor and then capacitor. Also called a resonant circuit, a tank circuit, or a tune circuit. Your LC circuit can act as an electrical resonator, an electrical analog of a tuning fork, storing energy oscillating at the circuit's resonant frequency. Your LC circuit is used either for generating signals at a particular frequency or picking out a signal at a particular frequency from a more complex signal. This function is called a bandpass filter. You will learn more about these filters when you go to higher electronics classes. Now let's take a look at here, this LC circuit here with this current I flowing in that direction. Initially, the capacitor here is fully charged with a voltage Vm, and with an initial charge of Q is equal to C times Pm. The moment your circuit is closed. The moment your switch is closed, the capacitor begins to discharge through your inductor. Your charge flows from your capacitor, but again, you have your inductor here, which resists the increase in flow of your current. So what happens is, your current builds in time. At maximum current, charge flow now decreases through your inductor. However, your inductor now resists your decreased flow and keeps pushing charge in the original direction. Now let's carefully analyze your LC circuit with these images here. In the beginning, you have a capacitor that is fully charged with zero current, and then you have here your capacitor. So in this sense, the circuit's energy is all stored in the electric field in your capacitor. At time equals 0, you close your switch here. As you close your switch, the capacitor starts discharging in your inductor. Initially, again, the capacitor, which is fully charged with voltage Vm and initial charge of Q is equal to C times Vm. The moment you close the switch, the capacitor begins to discharge through the inductor. Charge flows from the capacitor, but the inductor resists that increase in flow. Your current builds in time. It starts at 0, and then eventually it builds up to a maximum value, which is your Im. During this build-up, the capacitor is discharging. So as your current is building up to maximum Im, your capacitor here discharges. At each instant, the capacitor potential equals the induced EMF. So as the capacitor discharges, the rate of change of current also decreases. When the capacitor potential becomes 0, after fully discharging, the induced EMF is also 0, and the current has leveled off at its maximum value Im. The capacitor has completely discharged. The potential difference between its terminals and those of the inductor has decreased to zero, and the current has reached its maximum value, Im. Now, after the capacitor is fully discharged, the current is at maximum, and the circuit's energy are now all stored in the magnetic field. So initially before, all the energy is stored in the capacitor, in the electric field in the capacitor, and after your capacitor fully discharges, all the electric field now is stored in your magnetic field. This is at time that's equal to 1/4 of t. During the discharge of the capacitor, the increasing current in the inductor has established a magnetic field in the space around it. And then the energy that was initially stored in the capacitor is now stored in the inductor's magnetic field. This is the image that we were left in the previous slide, wherein your capacitor fully discharges and the circuit's energy is now stored all in the magnetic field. Although the capacitor is fully discharged in figure B, the current here, which is a maximum, persists and it cannot change instantaneously because again, you have your inductor here. So what happens is the capacitor begins to charge with the polarity opposite to the initial charge. So as you can see, because the current persists in your circuit here, your capacitor begins to charge. However, it is charging with the polarity opposite to the initial state. As the current decreases in your circuit here, inducing an EMF in your inductor in the same direction as the current, this slows down the decrease of the current. Eventually, the current and the magnetic field reaches zero, and the capacitor is now fully discharged in the sense opposite to its initial polarity. If you have observed earlier, this side here was your positive plate, and then this side here was your negative plate. But as soon as your capacitor charges in the opposite polarity, this now here is your negative plate, and this is your positive plate. The capacitor is now fully charged, and the current here is now zero. The circuit's energy is all stored in the electric field. So there was a change from this in the storing of your energy from the magnetic field again back to your electric field. So we have this one here, the last image in our previous analysis. What happens here is that since this capacitor is again fully charged and you're still connected with your inductor, your capacitor will now again begin to discharge in the opposite direction. So it will now discharge with the direction of your current here. The process now repeats in the reverse direction a little later. The capacitor has again discharged with this one here, and the energy is now again stored in the magnetic field. And as you can guess, since there is still this current in the inductor, this current persists. So what happens is it will again charge your capacitor in the opposite polarity. So this is your process, which is a cycle if there are no internal resistance in your inductor. So you begin with this one, the capacitor fully charged, and take note here of the polarity. This is your positive plate. You have here your negative plate. As you close the switch, your capacitor discharges in your inductor, and then this sets up the magnetic field here. Your capacitor is now again fully discharged. However, since the current persists, your capacitor will charge in the opposite polarity. This time, this is your negative plate, this is your positive plate, and your capacitor will be fully charged with your current now 0. Since this is now fully charged and you're still connected with your inductor, you guess that your capacitor will discharge in this direction to your inductor. Now your capacitor is fully discharged, but you have this current here that still persists. So the current will decrease, but as the current is decreased, your capacitor is charged again, going back to this circuit here. Now this process will go on unless you disturb your circuit. Still later, the capacitor charge returns to its original value and the whole process repeats. There are no energy losses. The charge and the capacitor continue to oscillate back and forth indefinitely. This process is called your electrical oscillation. There is a virtual lab activity for this one so that you can observe the current in your LC circuit. Please do the virtual circuit lab activity at Wellstud. Now let us analyze the current and charge as a function of time in your LC circuit. We'll do a Kirchhoff's loop around the circuit in the direction shown here. Remember that your current I can be positive or negative as it changes your as it changes direction as your capacitor charges, discharges, charges, discharges. And remember that your capacitance C is equal to Q over V. And from this loop here, following this direction, you have negative L d over dt, the voltage drop in your inductor, minus Q over C, the voltage drop in your capacitor, which is equal to 0. Now, since your current I is equal to dq over dt, it follows that your di over dt is equal to the second time derivative of your charge q. So you have d squared q over dt squared. So we substitute this one in the expression here and divide by negative L to obtain the following equation. You have a second degree differential equation, which is your d squared q over dt squared plus 1 over LCQ is equal to 0. And if you're familiar with simple harmonic motion, this one here is actually a simple harmonic motion with a standard solution. So you can solve this one already. This equation is similar to the simple harmonic motion of pendulums and springs. Now the standard solution for this one is given by this equation here. Solving for Q, you have Q is equal to your BQ times cosine omega t plus phi, where here your omega is your angular frequency of oscillation that is given by your omega that's equal to the square root of 1 over LC. With the same equation here, take note that the instantaneous current I is equal to dq over dt. Taking the time derivative of this equation, we have your d over dt here, and then also on this side here, you get your current I is equal to negative wq sine omega t plus p. So we just take the time derivative of this one, where you have the derivative of cosine, which is negative sine. The charge and current in an LC circuit, as you can see here, oscillates sinusoidally with time. You have a sine term and a cosine term. with an angular frequency determined by the values of L and C. To see the graph of the current, please do the virtual lab activity. So this is your comparison for electrical and mechanical oscillations. As you will see here, your capacitor charges discharges in your inductor. There's a change in the direction of your current. This is similar to your pendulum here, provided that there are no internal resistances in your circuit, and in your pendulum, this will oscillate uh, for eternity, or unless you disturb your circuit. These are some comparison. Your magnetic energy, 1/2 Li squared. This is similar to your kinetic energy, 1/2 mv squared. Your electrical energy, Q squared over 2C, is comparable to the potential energy, 1/2 kx squared. This is the energy conservation. This is the angular frequency. And this is your Q and X. In our discussion of the LC circuit, we assumed that there was no resistance in the circuit. Thus, you have your sinusoidal terms. This is actually an idealization, of course, because every real inductor has resistance in its windings. So even inside your inductor, there is resistance here. And there may be resistance in the connecting wires, of course. An ideal LC circuit exists only in the superconductivity domain, which is at very low temperatures. And LRC is the one that is seen in everyday circuits. So an LRC, or others say your RLC circuit, is an electrical circuit consisting of a resistor, an inductor, and a capacitor connected in series or in parallel. For this lesson, let us just discuss your LRC in series circuit. The RLC circuits have many applications as oscillator circuits. For example, you have radio receivers and television sets. Use them for tuning to select a narrow frequency range from ambient radio waves. So the way your radio and television sets are tuned is by using your RLC or your LRC circuits. An RLC circuit can be used as a bandpass filter, a bandstop filter, a low-pass filter, or high-pass filter. You will learn more about these applications in higher electronics classes. Because of resistance, electromagnetic energy in the circuit is dissipated and converted to other forms, such as the internal energy of the circuit materials. In comparison with this one here, you have a spring. Of course, if there is no internal resistance, this spring will oscillate forever, thus a sinusoidal current, or a sinusoidal change in your Y. However, if there is, of course, in reality, there is internal, or there is resistance in your surrounding, and there's also this pull of gravity here. So there's this gravity, okay, it stops this spring from oscillating forever. So this spring will of course stop at some time t, and you'll observe that the change in y becomes like this. So y decreases as time increases, and this is similar to your LRC circuit. Resistance in an electric circuit is analogous to friction in your mechanical system. So these are some of the changes in Q, your charge Q in your LRC circuit. As before, the capacitor is charged It starts to discharge as soon as your circuit is completed, just like in your LC circuit. But because of losses in your resistor, the magnetic field energy required by the inductor when the capacitor is completely discharged is less than the original electric field energy of the capacitor. So instead of having a sinusoidal term, what we have here is an underdamped circuit. So it does not anymore reach the maximum Q. So it loses your Q as time goes by because, of course, of your resistance R. If the resistance is relatively small, the circuit still oscillates like this one here, but with damped harmonic oscillation. If you have large R, the circuit cannot anymore oscillate. So this is a critically damped circuit, and then you have an overdamped circuit. Let's analyze your LRC circuit, your series circuit in more detail. So you have this one here. You have a source of EMF to charge your capacitor, and then you have your resistor and then your inductor. At the beginning, we are first charging your capacitor with your EMF here. We close the switch in the upward position, connecting the capacitor to the source of EMF for long enough time to ensure the capacitor acquires its final charge Q. That's equal to C times E, and any initial oscillations have died out. Then at time equals 0, we flip the switch so that it will now connect your lower circuit. So this one here will now be open. Removing the source from the circuit and placing the capacitor in series with the resistor and inductor. Now your capacitor will begin to discharge in your resistor and then your capacitor. To find Q and I, which vary with time, we apply your Kirchhoff's loop rule. To find how Q and I vary with time, we apply the loop rule, and starting at point A with this current direction here, you have minus IR for your resistor, minus L di over dt for your inductor, and minus Q over C for your capacitor. These are again your voltage drop across your circuit components. You don't have any other components, so that's equal to 0. And this is your equation here. Now, let's replace I with dq over dt. And rearranging this equation here, after replacing dq over dt, we get your second degree differential equation, which is your d squared q over dt squared plus r over L, dq over dt plus 1 over LCQ, that's equal to 0. There are general methods for obtaining the solution of the differential equation here. And note that when R is 0, this equation just reduces to your LC circuit. The form of the solution is different for your underdamped and your overdamped cases. Now let's look at when R squared is less than 4L over C. The solution of this differential equation has this form here. You have Q that's equal to AE negative R over 2L T cosine times square root of 1 over LC minus R squared over 4L squared T plus P, where A and P are constants. Now this solution corresponds to the underdamped behavior, where the function represents a sinusoidal oscillation with an exponential decaying amplitude. You have this sinusoidal oscillation given by your cosine. However, your oscillation exponentially decays because of this exponential term here. So what happens with the oscillation in your LRC circuit is like this. It oscillates sinusoidally, but since you have an exponential term, your oscillation is exponentially decaying as well, given by this exponential decays here. This is the solution for your underdamped circuit. Now, the angular frequency omega of the damp oscillations is given by this one. So you have omega prime is equal to the square root of 1 over LC minus R squared over 4L squared. This is for your underdamped LRC series circuit. But when R squared here is equal to 4L over C, the quantity under the radical becomes 0. So this one here becomes 0, and the system no longer oscillates in the case of the critical damping has been reached. So your cosine term will disappear, and you only have your exponential term, which is when you're going to graph your change in your Q, this is what happens. You have critical damping. For still larger values of your R, the system behaves as the circuit is overdamped, and Q is given as a function of time by the sum of two decreasing exponential functions. You can compare this one again with your spring, as you can see. But if you overstretch your spring, it will not anymore oscillate like this one here. Or you have also this overdamped circuit here. Again, if you can imagine your spring earlier, this is its oscillation. But if you exert a force that is greater than the force constant of your spring, it may not anymore oscillate. It will be critically damped with larger values of your force. This is what happens. So that is your LRC in your series circuit.